Hi class, we're beginning section 1.2 and we're going to continue the discussion about limits and how to calculate them, and there's some limit properties that we can use to help us while we're figuring out the limits of functions. We're also going to discuss the concept of continuity and what it means to have a continuous function. So let's get started by looking at the limit properties. One thing we want to make note of is that the limit of f of x exists as x approaches a, and we're going to call that L, and that's referenced down here in all of these rules. And we also have the limit of a function g exists, and we're going to call that M. And then we're going to have c being any constant. And so those are the three givens that we're assuming exist when we're talking about all of these rules. And so we're making sure all of these functions have limits where we're talking about them. And basically what these rules say is that if you have a constant function, the limit is just that constant itself. If we have a limit of a function which we know already, and we're taking it to the nth power, then we can replace that with the limit that we know and take that to the nth power. And then if we're adding two functions together and we want to take the limit of the sum of the functions, we can take the limits of each of those functions individually and then add them up. And so the addition or subtraction inside the function turns into addition and subtraction of the functions after we've taken the limit as well. The same thing with multiplication, the same thing with division, and the same thing as this one, which is typically the same as L3 or L4. It has the multiplication right here, but one of them is a constant and one of them is a function, and it's just the same thing. You can do that, pull the limit in and take the limit of each of those individual functions themselves. We're going to practice that coming on up. One statement that we should make before we begin is that the limit of x as x approaches 5 is going to be 5. And we're going to use that fact as we are moving along through the limit properties. So let's break down. We have first the powers. That's going to be the limit property 2. And so let's see. The limit of x squared as x approaches 5 is going to be the same thing as the limit of x as x approaches 5, the whole thing squared. Well, we know that that limit is 5, and 5 squared is 25. Next we have 2x, which we'll call rule L6, and that is the limit of a constant times a function as x approaches 5 is the same thing as the constant times the limit of x as x approaches 5, which would just be 2 times 5. In other words, that's 10. And then we have the constant at the beginning. So that's the limit of -3 as x approaches 5. That's just the constant, -3. And then we have the rule where we can combine all of these. That would be L3. So if I'm doing L3, that tells me I can take the results here, here, and here and add them all up together. So I would get 25 plus 10 minus 3, which gives me a limit of 32. So my limit as x approaches 5 of x squared plus 2x minus 3 is 32. While those limit properties are helpful, it can get a little bit tedious to do each portion of the polynomial that way. And we actually have theorem 2 to help us whenever we have polynomials or other rational functions. And so theorem 2 says that if you have a rational function f with an a value in the domain of f, then your limit of that function as x approaches a is the same thing as plugging a into that function itself. Rational functions include all polynomial functions, including constant, linear, quadratic, and ratios composed of such functions. So let's go ahead and do another problem similar to the first, but using this as our rule instead. If we're asked to find the limit of this polynomial function 2x cubed plus 3x squared minus 6, we first recognize that this is a polynomial which falls under the heading of rational functions, and that the domain should be all real numbers, so as x approaches 1, 1 is within the domain. Therefore, we can use this rule, and we can just say, what happens when I plug 1 into this function? So I get 2 times 1 cubed plus 3 times 1 squared minus 6, which is just 2 plus 3 minus 6, and there you get negative 1. So the limit of this function is negative 1. For video example 3, we notice that this is the limit of a rational function, and in the numerator and denominator, those are both polynomials. And let's just check, if we're doing the limit as x approaches 4, we have to make sure that when we plug in 4 to that denominator, it does not make 0. And it doesn't. So we can go ahead and solve this limit by plugging that value of 4 into the function. So then you're going to plug it in, say 2 times 4 squared plus 5 times 4 minus 1 over 3 times 4 minus 2. And so you get 2 times 16 plus 20 minus 1 over 12 minus 2. And then that becomes 32 plus 20 minus 1 over 10, which becomes 51 over 10. And we prefer our answers in reduced form, but also improper fractions rather than mixed numbers. So my limit here would be 51 over 10. Now if you review our limit properties, it might not seem like we've discussed how to deal with radicals. But radicals are just another way of writing exponents. Recall that if I said the square root of x, that's the same thing as x to the power of 1/2. And the cube root of y would just be y to the power of 1/3. And so if I have something like this, it would be to the power of 1/2. Let's go ahead and approach this using that as a power. According to L2, we are able to take that power and do the limit of the function inside. So this is going to be the square root of the limit as x approaches 2 of the phrase 1 plus 3x squared. And then that's a polynomial function, which is a rational function. So I can find that limit by evaluating that function at 2. And so I'm going to get 1 plus 3 times 2 squared. And then we get 1 plus 3 times 4, which is 1 plus 12. So you get radical 13 as your answer. So the limit of this is the square root of 13. At first glance, we might think that we can find the limit of r of x by doing the same thing. Let's just plug negative 3 into r. But when we do that, we should notice that you get negative 3 squared minus 9 over negative 3 plus 3, which becomes 9 minus 9 over 0, which becomes 0 over 0. Well, what is 0 over 0? That's what is called indeterminate. When we have something that is indeterminate, you can't use that to find your limit. You have to find your limit another way. Sometimes we can do this through algebraic simplification. That is, if you look at r of x, and we factor the numerator, we realize that algebraically, if I simplified it, it's going to be the same as x minus 3 everywhere, except for when x is equal to negative 3. That means that if I plugged negative 3 into this function, I would get a value, but when I plug negative 3 into this function, I got 0 over 0. It's indeterminate. However, because this reduced function is almost equivalent to the original function almost everywhere, then the value as it's heading towards that indeterminate spot would match the value that it's heading in general. It's hard to imagine what I'm saying without looking at the graphs, so I pulled up desmos.com to help us visualize it. Basically, when you see the graph of x squared minus 9 divided by x plus 3, it's this red line, which you can't really see, but there's a hole on the graph at -3, -6, right here. So you can see that when we get to this hole, it says -3 undefined. You can't figure out the value of the function at -3. But when we take a look at this green graph, which is just x minus 3, algebraically simplified, it's the exact same graph, except for when we go to that spot, it gives me a value at -3, -6. The difference is that the red graph was undefined at -3, while the green graph has a value of -3, -6. So that's why the graphs aren't exactly the same. However, they're the same everywhere else, and they lead to the same spots. By that, I mean that the limit of r of x as x approaches -3 is going to be the same as the limit of the simplified function x minus 3 as x goes to -3. Since the graphs were the same everywhere, they would lead to the same spots, and I can just evaluate this algebraically, simplifying it and then plugging that value in. And so then we get the limit would be -6. It's a common error that if you evaluate it and you get indeterminate, then you might think that the limit does not exist. But recall that we're not actually finding the value when we plug in the number. We're finding the value when we plug in numbers close to a, not necessarily a itself. That's why we can simplify this and plug the values in here and see where it's headed. It was headed towards -6. For this next example, notice that we're trying to find the limit as x approaches infinity. However, with this polynomial function, it's really hard to plug in infinity, just like we have been plugging in the values that we're approaching for all of our other examples. How do you plug in infinity? Well, that's weird, except for the fact that we do have one fact at our disposal. We don't know how to plug infinity into this function over here, but we know that the limit as we go towards k over x, where k is any constant and x is the denominator, as my denominator goes towards infinity, this fraction gets smaller and smaller and smaller, and so it goes towards 0. So we're going to use that fact for this question right here. We're going to take this function that we want to find the limit of and multiply it by 1 over x cubed on both the numerator and denominator. That's like multiplying by 1. Our limit rule, or limit property 3, tells us that we can take the limit of each of these individually, and so then that's the constant rule, and then this is going to be 0, that's going to be 0 squared, that's going to be 0 cubed, and so basically we end up with 2 plus 0 plus 0 plus 0 over 3 plus 0 minus 0. And so you end up with the limit being 2/3. You can always do this anytime you have the limit going to infinity. You can simplify this and make it into something that we can figure out. Looking at video example 7, we see that we're taking the limit as h approaches 0, and this is different from the limits we've been taking before. But you have to pay close attention to the notation over here. And we have a function that has two variables in it. It has an x and an h. So what do we do with that? Well, we're talking about the h being the variable. Everything else is going to be treated as a constant. And so when you have a limit, you have to pay close attention to the notation and to which variable is approaching which value. And so for here, we're going to take that limit. The 2x is considered a constant. You have a constant x plus that h is going to approach 0. And so you end up with 1 over 2x squared. And so this would be the limit. Pay close attention to your variables. The idea of continuity can be simply explained that if you're drawing the graph of a function, you can draw it without lifting your pencil or without having any gaps in your line. But it's always good to have a rigorous definition, something that we can refer to and algebraically. So a function is continuous at x equals a if the function exists at a, or you can plug it in and find its value, if the limit exists at a, and if the limit and its function value are the same thing. So you're not having sort of a jump anywhere, and you're having the function continuous as it leads to it and as it goes through the value at a. Now that's continuous at a, but we also have it's continuous in an open interval I, meaning that a function is continuous in multiple spots if it's continuous at every spot within that interval. And so you can say a function is continuous over the entire real numbers if there's no gaps in the entire function. When you're given a definition and then you're asked whether a function meets that definition, what you do is you go methodically through that definition to make sure it meets all of the conditions. So if we want to determine if this function is continuous at x equals 4, the first thing we have to do is find if f of 4 exists and evaluate it. Alright, f of 4 exists. Then we have to find out if the limit as x approaches 4 exists. And it does, because we know that the limit of a polynomial function is the same as plugging it in. And then we have to ask ourselves, does the limit match f of 4? And it does. So therefore, this function is continuous at x equals 4. Visually speaking, we know that 2x plus 3 is the graph of a line, and you know that there's no holes in this line, and so it's continuous at this point, and it continues through that point. Once again, for video example 9, we're given a function and we're asked to find if it's continuous at x is equal to 2. And so what we want to do is first evaluate g of 2. So g of 2 exists, and it is 5. The next thing we want to do is find the limit as x approaches 2. Now because it's a piecewise function, we do have to check the limit from the left and from the right. And the limit of g of x as x approaches 2 from the left is going to be 1. That's by plugging it into this equation. And then we know that the limit of g of x as x approaches 2 from the right would be looking at this equation, and we would get 5. And so since the limit from the left and the limit from the right don't match, therefore the limit does not exist. And since this limit does not exist, therefore it can't fit the definition of continuous. Therefore this function is not continuous. And you want to say that g of x is not continuous at x is equal to 2. For example 10, let's go ahead and follow the definition of continuous once again. First of all, we want to find f of 3 and make sure it exists. And f of 3 would be 5, as given by this equation right here. And then we want to find the limit as x approaches 3 of f of x. And that's something that we did a little bit earlier, or similar to what we did earlier today. And we would get the same as the limit as x approaches 3 for x plus 3. That's this function reduced. And so you would basically get 3 plus 3, which is 6. So that limit exists. Now step 3 says, does the limit match the function? And the limit as x approaches 3 of f of x does not match f of 3. So although it meets condition 1 and condition 2, it does not meet condition 3, therefore it is not continuous at x equals 3. So you state f of x is not continuous at x equals 3. For example 11, the question is, is the function h continuous for all x? And so we want to take into consideration the fact that we do know some things about these functions before we're looking at it. And we know that this rational function is continuous everywhere except for where there is a hole in the denominator. So that is, it's continuous everywhere except for where x equals 5. We also know that as a piecewise function, we would want to test any boundary points. So really the only concerning point is what happens at x equals 5. So let's test to see if it's continuous at x equals 5, and if it is, then we'll know it's continuous everywhere. The first step to testing if it's continuous at 5 is to plug it in. Does h of 5 exist? Yes, it does, and we're told that the answer is 10. Does the limit of h of x exist when x approaches 5? And that's not looking at this one, that's looking at that one. We know that the limit exists for that, and we can take that equation and simplify it algebraically. So that would be equivalent to finding the limit of x plus 5. And so we can just evaluate that by plugging it in and getting 10. So we have h of 5 is 10, we have the limit is also 10, so therefore they match. And so because the limit matches, it satisfies all three conditions, and so therefore it's continuous at 5, and therefore the whole function is continuous. One way that you might see this written sometimes is CTS. So you might see it written, h is continuous for all x. If you see that CTS, you know that's an abbreviation for continuous. For this last question, we're asked about a water tank that is empty at time t equals 0 minutes. It's filling at a rate of 3 gallons of water per minute for 30 minutes. At 30 minutes, the tank is no longer being filled and a valve is opened, allowing water to escape at a rate of 4 gallons per minute. The volume of water in the tank V in gallons after t minutes is given by the Vt function. And so you see that there. Now we're going to find the limit as we approach 30 from the left-hand side. In order to do that, we're thinking about values less than 30, so we're looking at that equation. And so you're just going to say 3 times 30, which is 90. To figure out the limit of our function as t approaches 30 from the right-hand side, we're looking for values of greater than 30. We're going to plug into this equation. So you're going to get 210 minus 4 times 30. And so there we have it. We have the limit from the left is 90, the limit from the right is 90. Since the limit from the left and the right exist and they match, therefore the limit of the function overall is 90. And we have to make sure all word problems make sense. So when we look at this 90, we want to ask what unit should be on 90. And the unit on 90 should be the volume in gallons. So the limit at 30 minutes would be 90 gallons. There are more examples in the book. You can see an example that's similar to this. Make sure that if you need more practice that you're looking at the book, and when you look at the textbook explanation, it might make more sense to you. You want to get that extra practice in. So thank you very much. Have a good day, and I'll see you later.